Well, I think let's get started. I think some people might roll in as we in the next couple of minutes. But I just want to say a few words before. So before I introduce today's speaker, I just want to say that so this year we, as you can see, we've moved the starting time of the colloquium back an hour to 3:30. But it's a bit confusing because whenever we have the Israel joint colloquia, that's at 4. So I'm gonna consult with everybody and see if it makes more sense to hold it always at 4, even though that doesn't fit so naturally within the Technion schedule that starts on a half hour. But having said that, so today is our first colloquium of the physics department by itself of the Technion. And it's a great pleasure to have Anna Ijjas. I hope I pronounced that okay.
It's perfect.
Okay, good. And Anna actually was supposed to be the first speaker of last semester back in March, and but of course, you know what happened. And so, hopefully at some point we'll manage to, host her physically so she can visit, and we'll get to know her. But so Anna, she's originally from Hungary, and she did her PhD in Germany in theoretical physics, and she did a postdoc in Princeton, and then she was a Simons Fellow, which she did jointly in Columbia and at the Smithsonian Institute in Cambridge. And now, since last year, she's faculty at the Max Planck Institute in Hanover in the Albert Einstein Institute for Gravitational Physics. And today she'll tell us about Big Bang or Big Bounce, I think is the name of the talk. So. Oh, and I should say, I think if you want to ask questions, just barge in, and if I see that it's disorderly, I'll say something, and then I'll ask you to do it in the chat. But for now, just interrupt and let's try that. Okay.
Okay. Thanks very much. I'm just starting to share my screen. So it's a great pleasure to be virtually here and kicking off the colloquium of the term. The issue that I will be talking about is something that perhaps all of us is interested in, or I hope so. Namely, it's really the question, how did we get here? And what happened 13.8 billion years ago that caused what got us here? And so what's special about it is in cosmology is we know what the universe looked like today when we look at it. And it's strangely diverse. We know that whether we look locally or on larger scales, the universe is really full of structure around us. Planets, stars cluster, and planets cluster into galaxies. We know that there are strange objects out there as black holes. So everything but simple. It's really rich of structure, rich of diverse structure. And so you might be surprised to hear that all this started from something very simple. So this really rich structureful universe is, and this is the real big puzzle in cosmology, and this is also the whole subject of my talk and also the subject of early universe cosmology. How is it possible that when we look at the universe, and I really mean here look, by using in particular cosmic microwave background experiments that tell us how the very early universe looked like really short after an event that commonly is dubbed the Big Bang, then what one sees is that this hot plasma was entirely of energy, was entirely uniform, and with nearly no deviation from uniformity. And we know that since it's a relativistic universe, that the uniformity and energy density also reflects the uniformity, the extreme simplicity of geometry, namely that we live in, and that is what we also see today on large scales, that our universe is having, with respect to its space-time geometry, something which we call perhaps the simplest possible, perhaps the most elegant possible, namely spherical symmetric. That means it doesn't really matter where you are or which direction you look. Again, if you are on large scales, it's all the same. That's what we call a homogeneous and isotropic space-time, or more elegantly, Friedman-Robertson-Walker space-time. And if you ask,
sorry, how do you know that it was such uniform and flat outside of inflation theory and all this, by observation? How do we know that?
Oh, how do we know it by observation? We get to this. We know this because we have, and this is why we also know it, how perfectly uniform is. We have since the 1960s satellites. So it's a perfect question since this was introducing my next slide. What we observe is what satellite experiments really since Penzias and Wilson can observe is completely uniform background radiation in the universe. And we know that this radiation, so it was a prediction of standard Big Bang cosmology. Now it's important to know that standard Big Bang cosmology is everything but describes the expanding universe since nucleosynthesis, but doesn't tell us anything about the Big Bang. So it's an unfortunate name, what we call standard Big Bang cosmology. It's everything but the beginning or whatever was the beginning Big Bang. And so
but it does show fluctuations. It does show fluctuations.
We will get to that. Yes, we will get to that in a second. So what one observes is this background radiation that is left behind when the universe finally cools down around 300,000 years after this first event, let's say nucleosynthesis, but put it into what triggered the expanding phase. Then when the hot plasma is cooling down enough that the photons can escape the matter, then there is a curtain, a temperature curtain left behind. That's what we call the cosmic microwave background. And this is what we can measure. And when we measure the cosmic microwave background, the first what Penzias and Wilson measured is not this map. So what you see on this map, it's everything but simple, right? You see cold spots drawn here blue and hot spots indicated by red. So you would say it's not uniform. There's a lot of structure in it, right? But this is not true. In order to see this structure, you need satellites of the 20th century, the Wilkinson microwave anisotropy probe, starting with COBE, but then the Wilkinson microwave anisotropy probe, or latest, the Planck satellite experiments, and there are still ongoing experiments. And what they measure is really how small, so what is the average energy density? And what is the amplitude of the deviations from the average energy density in the temperature fluctuations? So how far do I have to, in some sense, zoom in? So there are two maps. The first map that I showed you is completely uniform. That's what Penzias and Wilson saw. A radiation that no matter where you look into the sky, which direction or where, it's everywhere the same. That's the cosmic microwave background radiation, 2.7 Kelvin. And then if you have better instruments, better telescope, which are really satellites, mainly. Now today we have ground-based telescope, but most of the measurement was done with satellite experiments. Then they know that they have to zoom in the map, but would say you have to have a sensitivity of at least 1 part in 100,000 to see these deviations from uniformity. So this initial radiation is so homogeneous that if you wish on the map, what you see is 100,000 times magnification to see the structure of these deviations from perfect uniformity and homogeneity, both in energy density and in the geometry from perfect spherical symmetry. And so what you see there is, and this is what we have to explain, and it's not enough. We of course can make a statistics of the anisotropy. So we know that it's the leading order extremely homogeneous. And then we also know that there are then deviations which have an average amplitude of 1 part in 100,000. But now you can ask is what is the statistics of this of these deviations from perfect homogeneity. And what we find is scale invariant. So not just that the deviations are very small in amplitude, but no matter how you zoom in on this map, on which scale where you look in the universe, you will find that is invariant of the length scale where you look, the amplitude of these fluctuations will always be the same 10 to the minus 5, normalized by the average energy density. And then you ask further, what is the statistics of the deviation, so to speak, second order statistics? Then you again find, and that's what we cosmologists call simplicity. It's not just scaling, nearly almost scale invariant, but it's also Gaussian. So the distribution of the deviations is Gaussian. And I believe all of you would agree this is perhaps the simplest possible distribution which you could imagine. At the very least, we think of that in cosmology. And this is really the challenge of early universe cosmology since the 80s at the very latest to figure. So the latest map comes from 2018. The first measurement of the cosmic microwave background was in the early 60s. The first detection of the anisotropy in the early 90s. So at the latest, since the 90s, we know that this is an observed puzzle. So in the 80s, people already thought if this is true, and we will get to this by there were theoretical hints that not just the large-scale uniformity is true, but also the deviations from large-scale uniformity are extremely elegant, nearly scale invariant and Gaussian. Then that's a puzzle, and that's a puzzle exactly for the following reason, because, and we have already heard of it. Yes?
Sorry, by Gaussian, you mean a Gaussian, just a simple Gaussian massless field theory?
What I mean is if you take the 3-point function of the fluctuations, then the statistics of it is Gaussian. Yes, you can think of the fluctuations as scalars.
Okay, thanks.
And so what really leads to the puzzle is, first of all, it's an obvious puzzle that our rich structure can be tracked back to something that is very uniform in a very simple but puzzling way. And where is this puzzling? Why is it puzzling? You might think, well, okay, it just started like that. And this is the usual picture, even though we don't know what happened there. We think that 13.8 billion years ago, and this is the standard view, there was an event that triggered the current expanding phase. And short of a better name, we have been calling it a Big Bang for 50 plus years, this event, but we don't have a theory of the Big Bang. The Big Bang is really a placeholder of an event where the theory of gravity and quantum physics should be unified. And because all the scales, length scales, temperature scales, everything, energy density cannot be described anymore by means of classical physics, in particular general relativity. So in order to understand this event, if it was a beginning, we need quantum gravity. We don't yet have a theory of quantum gravity. So the puzzle was, okay, without knowing what set everything into motion, can we explain the simplicity? And then the first answer was, with general relativity only, we cannot. And I will get to that in a second. So please hold why we cannot. And so the idea was, okay, there has to be something, a physical mechanism between this quantum gravity event and, let's say, nucleosynthesis, when the first element started to form, that explains the initial conditions that lead to this very uniform large-scale geometry, very uniform distribution, energy density, with precise distribution of deviations from it. And so the idea was, and this was really the ideas of the early 80s, well, perhaps the theory should have a particular feature, short of having a theory of the Big Bang. The particular feature of this theory should be that later was became known as inflation, that it should be insensitive, whatever the theory of the Big Bang is. So it should be insensitive to how we come out of this quantum gravity phase. We should have a theory that dynamically sets the initial conditions for the evolution of our cosmos, setting the initial conditions for nucleosynthesis, radiation domination, matter domination, and today entering the phase of dark energy. So in this sense, insensitive. At the same time, it should be extremely predictive, because independent of the initial conditions, you should have arrived at a phase of which we know how it should look like, namely what I was explaining to you, homogeneous energy density with extremely well measured and precise deviations from it, both in energy density and geometry. And this is a theory about Alan Guth and later Paul Steinhardt and Andrei Linde championed among the first as inflationary theory. And what was the main idea? So this is today also the leading idea of the universe. And it's very tightly embedded into this Big Bang idea. So the idea of inflation was the triggering idea. Let me emphasize it again, that it has to be theory that's insensitive to the initial conditions that is given to us by the quantum gravity event, which we call the Big Bang, because we don't have such a theory, and leads to a universe as we measure it in an early universe, baby universe, as we measure it in the cosmic microwave background. And so first I want to tell you, because I owe you this, why is it so strange that the universe was simple? Isn't somehow equilibrium of the initial energy density what one would expect? Well, cosmologically speaking, or just coming from general relativity, the answer is simply no. And why is the answer no? Well, for the following reason. We live in a relativistic universe, which means that our universe is characterized, unlike a Newtonian universe, by two dynamical scales. The one is simple, that we knew from Newtonian physics, and very often characterized by the scale factor. Here I will use little a to denote it. This is just the scale of physical distances that it was to measure with rods and clocks, and just normal classical physics. In Newtonian physics, we already measure it this way: how far are two objects from one another, and so on. But general relativity, we know, introduces a second scale, dynamical scale. Namely, it introduces that all interactions have a fundamental scale, or maybe a maximum distance at which interactions can be happening at a given time, given some particular slicing of our space-time. And this is what we simply call the Hubble radius, which is in a particular way related in our universe as described by the Friedmann-Robertson-Walker geometry. So one dynamical parameter only, namely the stretching, the scale factor, the Hubble radius tells us the rate of stretching in some sense, the logarithmic rate of stretching. It is to the Hubble parameter, namely the Hubble parameter is given as the logarithmic time derivative of the scale factor, and the Hubble radius, which really gives us the distances of fundamental interactions, is given by its inverse. And what general relativity tells us furthermore is that the two scales don't evolve at the same rate. And this is all the puzzle. This is really the one relation that one has to understand in cosmology or just capture to understand where all the trouble comes from getting from a simple universe to a complicated one, or understanding a complicated universe is emerging from a simple one. And this is this little parameter epsilon. And we know it's a relativistic universe, so it's not just that geometry. There are two fundamental scales, the physical scale and the scale of interactions. But we also know that the dynamics is very much determined, or it's uniquely determined by the stress energy content of the geometry of our patch, which I will very often call the Hubble patch, just by saying a patch of size of a Hubble radius. And that is encoded into this little epsilon parameter. So the dominant at any point in a Friedmann-Roberts, in a spherical symmetric universe as ours, a homogeneous and isotropic universe, the rate at which our Hubble radius, so the scale of fundamental interactions evolving, is given to the dominant stress energy content, which again, in a spherical symmetric spacetime can be characterized in terms of a perfect fluid, even if it's not a perfect fluid, since spherical symmetry is really imposing the perfect fluidness structure on any stress energy content. So we can characterize this dominant energy density by its pressure P and energy density. And the ratio of them is obviously a dimensionless parameter. We call it epsilon, the equation of state. And this equation of state parameter tells us how much slower or faster our Hubble patch or the Hubble radius is expanding as opposed to the scale factor. So we know that since nucleosynthesis, both the scale factor and the Hubble parameter is expanding, it's growing, Hubble radius is growing. That's the definition of expansion. But we also know that starting nucleosynthesis, first the universe was radiation dominated. So P over rho was 1/3. And then afterwards, it was matter dominated, and matter is by definition pressureless. So epsilon was just 3/2. And today we know actually that we actually have an energy density. The dark energy has negative pressure, so epsilon is 0. The pressure over our energy density is -1. So this is what we run through cosmic evolution, and we see it that in particular during radiation and matter domination, and this is really important, the Hubble radius is this epsilon is greater than 1, and that's all what is needed to know to see the trouble. So what's happening is that the Hubble radius is expanding faster than the scale of physical distances. So what this really means is we see a lot more of space-time. So we see a lot more of the stuff that wasn't part of the Hubble patch when nucleosynthesis started. That's what it means that we are radiation or matter dominated. And why is it a problem? Well, for example, for the spatial curvature is a big problem because it's really as simple as it sounds. If decelerated expansion means that the Hubble radius is expanding faster than the physical scales, than the scale factor, then what it really means is we should see more of the stuff that wasn't in contact with us. And when something wasn't in causal contact with our Hubble patch, then we would, of course, expect that it doesn't look like us. This is just really the simple. If something has never been in causal contact, then we should not expect a priori that it would equilibrate, it would look like us. But what we measure is e to the 60 Hubble patches, or 10 to the 28, 10 to the 29 Hubble patches by the time of today. So what our universe today entails, but e to the 60 or 10 to the 28 Hubble patches that were separate at this early time when the expansion started. And due to the deceleration, we see all of that. And we should not see that all look the same. And this is really—
Why? Can you please explain this? I mean, if you have the same dynamical process in all areas, doesn't matter that they don't come together. If I see a diffusion particle, I can see it here and there, I'll get the same statistics, whatever.
For two reasons. So the one reason is why it's simple, because that would mean that you synchronize all initial conditions over e to the 60 patches. And you have to explain why things are synchronized. But second, it's not just to leading order I synchronize. You asked me about the patches. If you ask, if I zoom in on a distribution on this cold spot and hot spot, some of them represent patches of space that were this, just one spot would represent actually several Hubble patches on space. So even the fluctuations that cannot be of classical origin, we know that. So you have to zoom in. 10 to the -5 is actually below of what could equilibrate classically. You see them being uniform. So we know that there cannot be any class. They are so uniform, it cannot be a classical equilibrating process. So you have two options. You have to come up with a quantum theory of gravity that explains this equilibration, or, and this was the idea of inflation, we want to explain it by somewhat leading order classical means. And then general relativity tells you that those e to the 60 patches or 10 to the 28 patches could only look the same if all independently had the same initial conditions up to 10 to the -5. Actually, today we measured 10 to the -10, 1 part in 10 to the -10 in deviations from the average energy density. And this is being considered a puzzle because we think, there are discussions about fine tuning, but we believe in cosmology that this is something that shouldn't be the case, because classically, by definition, there cannot be either it came out something like from the quantum process, or there cannot be a classical process unless perhaps inflation or slow contractions, I will show you, that equilibrated them. And then second thing is, maybe we get to first the classical one and then we get to the fluctuations. So it's really, I just want to illustrate you, let's say, matter domination. And what happens is, our little red circle is the Hubble patch, and the big ball is just space-time, and there are obviously parts of outside of space-time. And as we accelerate, as we expand at a decelerated rate, what the illustration want to show you is, for example, you see more of curvature, right? It is the same thing when you would, well, nowadays it's not happening that often, unfortunately, but if we used to depart by a plane, then we see more of the horizon. So some people call the Hubble radius sometimes, and it's a good approximation, also our horizon, a particle horizon or causal horizon. You would see simply speaking, the wider your horizon is, the more of curvature you would need to see. So your expectation would be, for example, if even a spherical symmetric universe could have spatial curvature. It could be open, flat, or curved. And there are infinitely more curved and open or closed universes, and there's only one flat universe. So we would expect that some patches started with spatial curvature, some patches started with open, some patches started closed, some patches might have started flat. But what we would not expect is that when we see e to the 60 of all of these patches, that is the answer, that all of them started flat, because there are infinitely many conditions that they should have started closed or open. So there are infinitely many options to be curved one way or the other, spatially curved, but there is only one option to be flat. So this is, in some naive sense, the explanation. There is no deeper sense in which cosmologists are troubled with this, that we don't understand why when there are that many options and things that didn't communicate it with other, why they would look the same. And so the idea of inflation was to restore somehow the notion that what looks the same started in the same condition. So what comes in later into our Hubble patch actually was originating at some point in the same Hubble patch. And this is why inflation was introduced. Can there be a mechanism that can start with a single Hubble patch and does the opposite as happening during decelerated expansion? So instead of letting stuff come into our Hubble patch, maybe letting stuff go out of this uniform Hubble patch, so that when after nucleosynthesis, when with nucleosynthesis deceleration start, the stuff that comes in is actually something that was in causal contact with us and had all the same origin. And this really is indeed a theory of inflation that Good, Steinhardt, and Linde introduced to leading order. We see everything looking the same because everything is having the same origin. And they really took it seriously. What I was trying to convince you is at the heart of the problem, that we need a stress energy content that somehow freezes in the initial Hubble radius or makes it expand very slow. That's what people call de Sitter-like or de Sitter expansion. So your Hubble radius is hardly moving. That would be exact de Sitter is not moving, or slowly expanding, very slowly. So H dot is nearly zero. At the same time, and that's where the accelerating expansion comes in, your scale factor is rapidly expanding. So when epsilon is much smaller than 1, really close to 0, then you have a really frozen initial Hubble patch and things are just flying out of your Hubble horizon. And so what you see is the opposite. So the inflation should be the inversion of decelerated expansion. You start with a Hubble patch and the Hubble patch almost retains its size and the stuff goes out of physical distances, everything goes out of your Hubble patch. And so at the end of the inflation, you have almost the same size of the Hubble patch, but there are e to the 60 other Hubble patches outside of your Hubble patch that looks exactly the same. And these will be the Hubble patches that you then get to see during the phase of decelerated expansion. So this was the idea of inflation. And this is today what people believe one of the strengths of inflation, to say things look the same because they actually started out in the same state and we just lost sight of it. And during deceleration, we again gained sight of what we couldn't see. Now, there is another feature, because now I explained you or summarized you the explanation of why things should look to leading order the same. But we also know that there would be no structure at all if everything would be exactly the same. So what you also want to see is really where do these instabilities come from? It turns out that inflation is such a powerful smoothing process in the sense that no classical deviations from the energy density would survive. So you would end up with a perfectly stable universe. At the same time, we also know that even in the early universe, quantum fluctuations don't go away. So they sit on top of locally, they sit on top of your curved background. We know that locally, via Einstein gravity, they see a flat background, a Minkowski background, and we have quantum fluctuation in all degrees of freedom, both in the scalar degrees of freedom of the metric or of space-time in the vector degrees of freedom, and also in the tensor degrees of freedom. Now, the good part of it is that what was discovered is that actually inflation can, when of fluctuation of quantum origin during an inflationary background, will be also stretched over superhorizon scale. So when they re-enter our Hubble patch, they can be the seed of small deviations from the total energy density, and then later the seed of gravitational collapse and clumping and structure. At the same time, there is another problem that first, again, Steinhardt pointed out in '83, then later also was confirmed by Vilenkin, and is today known as one of the main features of inflation. I'm really calling it feature because you might like it or not. I personally don't like it, and that will be one part of the reason why I'm not working on it. So we will get to this. This is what's called maybe I believe many of you have heard of the multiverse problem, or the multiverse feature of the inflationary multiverse. Now, it turns out that if you really study the fluctuations of quantum origin, that should be leading to the cosmic temperature anisotropies of the microwave background by way of generating curvature fluctuations in the initial geometry, then something is obvious. First of all, this is a Bessel. You might see that this is a Bessel-like equation. The first approximation. If I tell you that typically the scale factor scales the power law with the time, then you also see it's indeed a Bessel equation for every mode of density fluctuations, curvature fluctuations in the initial plasma. And what you also see is if A double prime is positive, which is a definition for inflation of accelerated expansion, there is a fundamental instability in this equation. And this is called the quantum instability of inflation. And so what really happens is that the linear approximations, we believe, and this is how we do our calculations, and this is how the early inflationary protagonists introduced us to this calculation was, take this equation, take this Bessel equation, compute the spectrum that you would get for the fluctuations in the scalar curvature, compute what kind of temperature fluctuations this would cause, and compare it with data. And it turned out that this looks great. This really exactly is matching what we see in the cosmic microwave background on the one hand. On the other hand, there's also this instability, which means that there is some strong coupling emerging. There's something that this linear approximation won't be your leading order approximation. This is not the true description of the story. The non-linearities are just around the corner. So what did the early inflationary, and up until today, what do people do? Well, they choose shapes of the potential, the inflationary potential that should source the equation of state that triggers the sitter-like expansion, such that these non-linearities are so far, in some sense, in field space beyond the potential shape that they are invisible for the length of inflation that's relevant for our observable universe. So once again, what it means is, I was talking about it, we need 10 to the 28 Hubble patches or 8 to the 60 Hubble patches. So we very often call it 60 E-folds of inflation. So the shape of the inflationary potential that sources the stress energy to trigger inflation is chosen in a way that this instability, the nonlinearities don't have time to evolve during the 60 efforts. So it's some sense invisible to us today that there are these nonlinearities because there is this fundamental instability. That doesn't mean though that patches in space-time that inflate longer, and we know that they are out there, would not see this instability. And this is really what's called the multiverse problem. Because what it leads to is what people discovered really since the 80s, and then nowadays it's especially by Linda and Good championed as the leading feature of inflation, that inflation is eternal. So Good says, simply speaking, due to these nonlinearities, there will be always patches of parts of space-time that are inflating. As a matter, they don't finish inflation in 60 folds due to quantum fluctuations, so on the part of the potential that feels these nonlinearities, that part of space-time won't stop inflating. So on the one hand, it's invisible to us. On the other hand, we are sitting on a classical aisle, and around the space-time is still inflating. And it's inflating in a way that is not anymore what you would think about it as leading to our universe. So it doesn't just simply inflate in the same way as our universe would be inflating, but it's inflating in a way as leading to our universe. But these rare quantum fluctuations that keep inflation going, so these nonlinearities that are not characterized anymore by the same spectrum as our of fluctuations as our cosmic microwave background, lead to fundamentally different universes. So simply speaking, to quote Guth, inflation, the most generic feature of inflation is that it's eternal, and which meaning that anything that can happen in an inflationary universe will happen, and it will happen infinitely often. So how does it look? We start with a Hubble patch, which is completely homogeneous. And you see the little islands that are coming down are all universes. One of them is ours, finishing inflation. So on the upper part of this plot, everything is inflating. And so the ideal situation would be this: inflation leading to one universe looking like ours. But due to this fundamental instability, the parts of the potential that feel in space-time that are dominated by that part of the potential that feel this instability will lead to different ends of inflation with different spectrum of fluctuations leading to different universes, which is what does it mean? Well, there will be universes that are curved. There will be universes with a microwave background spectrum that is far from being scale invariant, is far from being Gaussian. Some will be open, some will be closed, some will be very non-Gaussian, some will be very non-scale invariant. So the bottom line is, and most of space-time will be inflating. So if it's true, then most of space-time is actually still inflating, with lots of islands being classical, having finished inflations, but all of them look the same. So that's where Good comes in, inflation exploring everything what's possible classically and quantum mechanically, and also realizing it. And this is now a problem, if you wish. So there are really two groups, or three, in cosmology, how to look at this. There is no disagreement about the fact that the inflation has this feature, but there is a disagreement about it. What should we do about this? And first of all, the disagreement is coming from the fact that we can hide this feature. So if we tune the potential, as has been done since the 80s, mid-80s, then first of all, we will never have to care in some sense about this feature, because our space-time, it is hidden from us. The nonlinearities are hidden from us. We can just follow this linear equation and make predictions from microwave background. On the other hand, there is this other problem that how do we know that we make the right kind of predictions? Is it possible? And the answer is uniform among cosmologists within an inflationary multiverse to make predictions. What is a typical universe? Because the initial idea was inflation should be insensitive to quantum gravity and it should generically lead to a universe like ours. But what people figured is why locally it might lead to a universe that looks like ours. On a global scale, it leads to infinitely many universes, infinitely many of which look very different like ours. And worse, we know today that there is no possibility to introduce a measure. So we don't know what's typical in a multiverse. And therefore you might say, and many astrophysicists do that, well, this is metaphysics. And while there is nothing wrong with metaphysics if it's done in philosophy department, physicists just would forget about this feature. And I would say just calculate the inflationary predictions in terms of the linear theory, propose potentials, compare it to the microwave background, and live with it. And I would say this is perhaps the standard view in cosmology. And there are two other views, and this is a standard view of people who mostly do the observations. And there are two other views, people who, I would say the proponents of inflation, the theorists say, well, actually this is great, because now we never have to ask any question what can happen. If our universe is possible with an inflation, then it can happen, and inflation indeed explains it. So these are the people, I would say, let's say the Stanford group, especially in the US, who would say, well, we take this seriously, and this is really the prediction of inflation. And so when, for example, the microwave background polarization was being measured in 2014, and a team BICEP 2 was reporting that they have seen not just the temperature fluctuations, but also the polarization of the microwave background, we will get to this in a bit, then people were celebrating it as a proof of the multiverse. And then the Planck catalog was 2013 shown, then the Planck PI Georgiev statue was also hinting that this is now evidence for the multiverse. So that is the third, and then there's the third group, and I would say I'm part of that group definitely, who says, well, we should be able to do better. Namely, why don't we go back and ask, can we perhaps really fulfill the original wish? Can we have a cosmology that generically, that explains in a physical sense why most initial conditions should lead to a universe like ours? Why somebody who asks what kind of universe you find ourselves in should have the answer, our universe should be typical. So our universe on cosmological scales in some sense should be typical. Namely that for most cosmic initial conditions, we should get our universe. And what do I mean by this? Well, first of all, what you want to show is that if you choose some initial distribution of energy density and spacetime, and we will get to it what initial is. Does it mean a Big Bang? Does it mean quantum gravity or something else? I will plead for something else. Then first of all, what I have been talking about, we have to get an FRW background, which means spatially flat, homogeneous isotropic geometry with curvature fluctuations transforming into later into temperature fluctuations, microwave background and series of structure, particular statistics. What we want to do more, at the moment we don't see any type of others. So while we see that density fluctuations were excited in the initial energy density, we don't see that gravitational wave or tensorial fluctuations were excited. So we will have to explain why they are not there. Second ambition is, well, we know that the Big Bang, and I have been emphasized, just a placeholder. We have to resolve this issue. So good cosmology will resolve that issue. And really that's where I want to stop and move immediately on to the picture that I want to present you in the second half of my talk is, we really don't want to have a theory that leads to a multiverse or has a multiverse problem, or more mathematically speaking, a quantum instability where the predictions cannot be trusted on global scales and where therefore you cannot make any predictions about the local universe with respect to its main features. Good. And so the picture that I will present you today is fundamentally different from Big Bang cosmology. And this is a picture where the main idea is being questioned that led to all the problems, why you needed inflation. Now, why did we need inflation? In some very simple sense, we needed inflation because we know that something had to happen before nuclear synthesis that in a very powerful way smoothed and flattened the universe and nevertheless allowed for a very particular structure of inhomogeneities in the original energy density and space-time geometry structure. And the second idea of inflation, and it should be insensitive to the bang. So you were left with a very little window where you had to squeeze in something called inflation, and that led to some issues such as the multiverse problem. And you ended up with a theory that cannot make you generic predictions about why you look today as you look. So one idea is perhaps, and at the same time, you couldn't resolve the singularity problem, right? So one idea is, and this is an idea that was there since we know that there can be an expanding universe, really in the original paper of Friedman, but perhaps the universe didn't have a beginning in the sense of a Big Bang. So this is no new idea, and really one shouldn't even just credit Friedman with this idea. The main idea goes back to old philosophies, Asian philosophies, but I would, some people even say that not even the Torah, but I don't want to become religious here since I have no, predicts a beginning. Maybe the right definition is maybe an ordering has started. So in that sense, maybe it's the most ancient idea we have. Maybe it is just with Christianity that the beginning came in, and this is not exactly, and we just wanted to enforce this idea on a physical picture, and maybe this is what we should give up. And so that is really the basic idea of what I want to present you. What if we give up a Big Bang and imagine that our universe didn't start, but what we call a Big Bang is really a transition from a previous phase where space-time shrank down to a certain size, contracted down. All the features of we see in the microwave background were generated in this contracting phase. So all the flatness and smoothness of the space-time geometry and the initial density fluctuations. And what transmitted this nice initial conditions, nicely prepared space-time patch to today is called the cosmological bands. And after the bands, starting with nuclear synthesis and so on, just how we know standard Big Bang cosmology would continue until today, until a few more Hubble times of dark energy inflation passed. Then this contraction would really start, universe would bounce, and expansion would again start. So this is the picture that I want to talk to you about, the cyclic universe, where all the features what we see today in the background and some evolve in a previous phase that is connected to us to our expanding phase by a bang, which is replacing the bands. Okay, so this is the one part that I will talk least about since I was invited to give a seminar in 2 days in the astrophysics or for the astrophysics group. Just let me just pan back a little bit and remind you what the problem was of the initial Big Bang cosmology, how inflation was supposed to solve it, and why inflation is not necessary for it. As I attempted to explain, the real problem of the early universe is not expansion versus contraction or whatever. The real problem is the rate at which physical distances expand as opposed to the Hubble radius. Because if the physical distances expand at a slower rate than the Hubble radius, then we get to see things that have never been in causal contact with us. And you see, this is not something that's important that you expand, because you might think, okay, what does she talk about here? Really, she wants to convince us that somehow if I contract something together, crunch something together that will smooth, that sounds like a crazy idea. By stretching, blowing up a balloon, stretching a rubber band, that seems okay. So that's wrong, right? For the same reason why Newtonian physics is wrong when applied to relativistic scales and relativistic speeds. We know that decelerated expansion is stretching. It's like blowing up the ball, but it's not smoothing space-time. Why? Well, because it's stretching at a wrong rate, at a too slow rate compared to the Hubble radius is stretching. And in the same sense, not all contraction is, matter-dominated contraction is clumping. That's really making things more messy. But if we have a contraction where the Hubble radius is shrinking in on all physical scales, then it's exactly the same idea and the same smoothing mechanism that inflation was supposed to do. Namely, the Hubble radius, so there the Hubble radius was almost standing still and stuff was going out, so that when stuff came again in during decelerated expansion, that had all the same origin. Now we do the same, just in some sense. How can one do it with contraction? Well, we do the opposite. We know that the Hubble radius shrinks, we know that the physical distances shrink, but what we want to do is, again, that all has the same origin. So what we do is, well, we have to shrink in the Hubble radius much faster instead of freezing it out. And if the Hubble radius hides us, so to speak, then we enter the expanding phase. What was there before, what all had the same origin, then it's exactly the same idea of inflation. So to this extent, inflation and slow contraction in terms of the physical scales contracting much slower than the Hubble radius, so the scale of fundamental interaction has exactly the mirror image of inflation. It's all the same idea. And I would say up until then, we are on the same footing. So if you look at it, what do I want? That this red patch is getting smaller and smaller and much smaller. So the red patch is the Hubble radius, and around it is space-time. And slow contraction means that this red patch, my Hubble radius, is shrinking much slower than space-time. So that at the end of the day, I have a very small Hubble radius, but hardly anything happened to my space-time patch. So if I enter the phase of decelerated expansion, things only comes into my Hubble patch that was already part of it before I started contracting. And there is one advantage. So far, I would say, and again, this is not that, unfortunately, and I would have loved if it's the case, but I'm just too young for that. It was discovered in the early 2000s by Steinhardt and Turok, that the mechanism of slow contraction, they called it back then for some reasons in what theory they embedded in of quantum gravity or string theory, expirative contraction, but it's really just meaning slow contraction in the sense physical scales contracting much slower than the Hubble radius. that this is smoothing in the same way as inflation. But what is the advantage of it really, and why it's worth considering this phase as opposed to inflation, or even if you think inflation is still a very good idea, this is fundamentally different with respect to how fluctuations evolve. Because what characterized inflation and what led to the quantum instability, and what was one of the triggers of the initiators of these studies, Turok and Steinhardt and collaborators, Ovrud, Kohuri, and so on, was exactly this trouble with the quantum instability coming from the fact that A double prime, so the second time derivative of the scale factor, is positive, accelerated expansion. Now in contraction is the opposite. Slow contraction means A double prime is negative. So instead of a quantum instability where inflation on global scales leads to universes dominating by the quantum nonlinearities during the inflationary phase that are fundamentally different than us, and they're out there somehow in this picture infinitely often and infinitely diverse, encompassing a continuum. Here your classical predictions remain their leading order predictions. So fluctuations of quantum origin that evolve according to this classical Bessel equation don't run away. There is no nonlinear quantum instability. And I think this is this is perhaps the most remarkable feature of the combination of slow contraction being a classical smoother, not leading to a quantum instability by definition. And now this is something that I'm working on right now, and won't spend too much time here because I want to spend an entire seminar on it on Wednesday. This is the idea, well, how robust this is to initial conditions. So one question was, and this is the last step, what I want to talk about slow contraction before I go over to the cyclic picture. How robust is it to initial conditions? I always was cheating a little bit during this entire colloquium because I was always giving both inflation and slow contraction a Hubble patch that almost looked like as it should look like. And I only explained to you why it becomes spatially flat and how lots of volume will look like ours when we enter the decelerating phase. But now you could ask is, but hold it, didn't you explain us that what the real idea was to be insensitive to initial conditions? So what good is it for if you give me a patch that almost looks like ours and everything what you can do is shrink in the Hubble radius on it or let the volume go out so that we see what has always been there during decelerated expansion? And you are right, that's actually really begging the question. This is an infinitely fine-tuned initial data in some sense, the relativists would say, because you almost choose the right kind of initial conditions. So on the one hand, it's necessary because if the theory didn't work for the right kind of initial conditions in the sense of making lots of Hubble volume of them, by the time this expansion starts, you could stop. But you cannot stop there. What you really want to ask is, okay, what is the next step? What happens if I go further away from the right kind of initial conditions? Does this mechanism still lead to a universe like ours? And the answer that I want to tell you, or those, of course, who are more interested in the details on Wednesday is, in the case of slow contraction, it's really the case. And what one needs for it is quite interesting, the same technology of numerical relativity and mathematical relativity that one uses to understand nonlinear mergers of compact objects, how one extracts, for example, waveforms for the gravitational wave measurements that are so popular today. So for now, and perhaps afterwards, if you want to have questions, I just want to show you how such a simulation look like. What you will see is different contributions to the energy density. Is there a question? Yeah, perhaps later. Okay. So what you see is a universe in a box. That's how we simulate it. And that we let in inhomogeneity, so shear, any type of deviations from the Friedman-Roberts from spherical symmetry, shear is green, and spatial curvature is blue. So those are the things that cosmologists are worried about. They can mess up the space-time geometry and the distribution of the energy density. And the matter that I will tell you on the next slides, what is sourced by, is the smoothing matter component, which is sourced by a scalar field, is the one that should come to dominate. And if it's homogeneous and dominating all other contributions to energy density, then you end up with a space-time. You can read it off from here that is smooth and flat. And the interesting thing about this is I very often say, in some sense, this is a simulation that you work on for a year or more with lots of people. And at the end of the day, you want to see the most boring result. It will be boring. So usually we do simulations to see some rich structure. But what we really want to see is we start with some weird initial conditions. Weird means not homogeneous, not isotropic, not homogeneous, you see the wiggles, not isotropic, you see the wiggles in the shear, not homogeneous, you see the wiggles in the curvature. And what you want to see that all those go to 0 because these are fractional energy densities. And what you see is that everything is dominated by a completely even scalar field matter, which is red, which is smoothing the universe. And I gave it away. This is really what you will see. And so I will tell more about this. You can do it 1,000, 2,000, really lots of times, depending on how many postdocs and students you have, under very different conditions. You almost always will the same thing. It's very rapidly smoothing space-time, even if you start very far away from Friedman-Robertson-Walker initial conditions. So in this sense, it is robust. But I want to tell you 2 more snippets. So if you now believe me that it is not just in the sense of information a classical smoother, as I explained in the beginning, if you start almost the right conditions, gives you lots of volume of the right conditions. It's not just avoiding the quantum instability, but it's also a robust classical smoother. Then you might think, okay, that's good. But there are 2 concerns that one might have. First of all, you might ask, but we are expanding. So how do I get to contraction from expansion? And how do I get out of contraction to expansion? And the remaining 5 minutes, I exactly want to tell you about this. So first of all, today, let's imagine, so the simple answer is getting from accelerated expansion, dark energy dominated expansion to contraction is simple. It's almost dark energy domination. What I want to convince you in the next 30 seconds is really, in some sense, you are on the verge to contraction, to slow contraction. So that's simple. And the hard part is really to balance, to go from contraction to expansion. And why is it simple? Well, today we are in a Friedman-Robertson-Walker universe dominated, we believe, by something that's called dark energy. We don't quite know what it is. We hope it's not a cosmological constant, because that doesn't really make physical sense. We would love to have a physical mechanism. So most of us think, at least let's for now model it with a scalar field that has some sort of potential. And then today's evolution is really described by 2 equations, because the Einstein equations really dramatically simplify in our universe to a constraint. The first one, which describes that the total energy density is relating to the geometry in this very simple way. The total energy density is giving the Hubble radius squared. We will work in Planck units here. And we even know that the evolution of the geometric, this Hubble radius, is given, as just I said, through the equation of state dominant stress energy content. So this is just where I started. And because we are expanding, the Hubble radius is growing, so it's inverse, the Hubble parameter is shrinking, and it's positive with cosmic time. Now it turns out, if dark energy, let's say, is a scalar field with the kinetic energy and the potential energy, then we know that the sum of them is the energy density, and the difference of them is the pressure. So we can simply rewrite the equation of state as being 3 times the kinetic energy of the scalar over its total energy density. Now you see, and as cosmologists always do, the simplest thinking of, well, today perhaps there is a constant part, that's what we measure. This is the dark energy density. So, and perhaps why not to assume that there is a negative potential? And why not is the following. Well, first of all, you see what's happening today, let's imagine that our scalar field is just sitting in a metastable state or rolling incredibly slow that we cannot feel it. And that's what's triggering dark energy domination. But if it's not a true constant, but modeled as we often do to a first approximation by exponential, you could take parallel, it is really just for simplicity. And because it's easy to calculate with it, then at some point, so no worries, it won't happen tomorrow, in a few Hubble times, so in a few 100 billion years, we will roll out of this phase, or whatever is left from us. And what's happening there is, so you see a constant positive potential will lead to a very slowly rolling field. The potential is overwhelming the kinetic energy. We know in the Klein-Gordon equation, the scalar field is experiencing this positive Hubble parameter, but Hubble parameter is very, very, very small, just positive. So slight friction, but it's really almost behaving like a free field. But at some point, it will start to experience the potential slope and will start to roll out. And what you see is at some point, so the potential is becoming more and more negative. And what's really happening is that the equation of state is becoming, instead of being close to 0, becoming approximately 3. The scalar will behave as a free field, picking up kinetic energy, hardly feeling anything from the background friction, which is given to the positive Hubble parameter. So like the background is in this sense acting, the gravitational background as a damping parameter on the field. And so what's happening later is as the potential becomes more and more negative, given the Einstein equation, nothing else can happen, but the total energy density goes to 0. And because the total energy density can never become less than negative, everything picks up. The friction becomes an anti-friction, so the Hubble parameter switches sign, and everything gets blue shifted. So the scalar field's kinetic energy is getting blue shifted. All energy densities are growing, and the scalar field is just going downhill on the potential energy density. What happens is the Hubble parameter switches from negative to positive. A dot crosses 0 and goes from the expansion to contraction, and that's what you get. So it's exactly the slow contracting phase that you want to have. If you have a scalar field that today is dominated by its positive small slope, but has a true negative minimal negative part, everything what can happen from dark energy domination is that you eventually roll over to slow contraction. So that's half of the business, and everything is according to Einstein gravity. You don't need anything else but a quintessence field. And those who work in fundamental physics, in particular supergravity, these potentials are the potentials that are popping out of those theories. Now, I'm not an expert, so I'm just quoting here those who work on it. And so as a last part, I just want to tell you what is the hard problem, what we are working on right now. Actually, with most of our research focus is this is the hard problem, because we know that while you can go from, you start radiation domination, matter domination, dark energy domination, and we know it's not difficult to get from dark energy domination to slow contraction. What's difficult is this. As a matter of fact, it's completely forbidden in Einstein gravity. We know that with any, as Penrose and Hawking have shown it, with any, as they called, reasonable matter. So with any matter that we know of, radiation matter, ordinary scalar field, within coupled to Einstein gravity, you cannot make, and this is what people call the null energy condition, you cannot make the Hubble parameter grow. And that is the challenge of a bounce. How do you make the Hubble parameter grow? How do you go from a phase of slow contraction with, at the end, very negative Hubble parameter to a phase of decelerated expansion that has to start with a very positive Hubble parameter? And there you have two options. You either have, this is what you have to do. You have to have a description of the universe where first you expand, then contract, and then bounce. Expand, contract, bounce. Expand, contract, bounce. And we know that we know how that works. Einstein gravity, but this is what do we have to do here. And two options are back to where you were with inflation. Just rest on quantum gravity and try to make a quantum bounce. So either a quantum beginning or a quantum bounce. And there are people who work on it, and I think it's important to work on it, but you have to be incredibly smart. And if you are not just as smart, and I perhaps would say I'm definitely not as smart, then you might try it. What can I do now without being particularly smart? And what you might want to do is, will lead to a cyclic picture with which I want to close is, you might ask, can I perhaps modify Einstein gravity where I know I have to modify it, namely close to the Planck scale, but not right at the Planck scale? Can I modify Einstein gravity in a way that it's still describable with dynamic or classical equations, it's still Lorentz invariance, it still maintains all the causal structure that I like about Einstein gravity, it still leads to predictions, it still solves the Cauchy problem, so it's where posits for given initial data, it leads to unique predictions. At the same time, can reach this bound, so which is said is violating what people call the null energy condition, which means if you project the stress energy tensor onto null vectors, then you remain positive. Here you cannot. Simply speaking, Friedman-Robertson-Walker space-time energy condition just means H has to decrease all the time. Can I do that? And this is exactly, I just have to assert what we have been working on now. We think we have a perturbative or stable solution, at least one. And we are trying to do exactly the same thing what we have been doing with slow contraction, putting it on the computer. And that is certainly a really big challenge because the structure of these equations, these partial differential equations, is complicated. They are nonlinear, they are coupled to one another, and we don't know them as well as Einstein gravity. So that remains a challenge. Once we're done with it, and we know that we are at least on the track, and if we don't hit any roadblocks to show their robustness, not just the existence of the solution, then this would lead to a picture that I want to close with. This is a very stark contrast with what I showed you about the global picture of inflation. So locally, inflation is very neat because it looks like as it leading to a smooth and flat universe where you don't have any idea of the quantum nonlinearity, since by construction we have theories that hide that from us by way of having appropriate shapes of the potential. However, if you look at the global scale, what's really happening is, and what's the true prediction of inflation is, what is space-time doing? And you see it's maximally unsmooth with lots of islands of classical universes exploring lots of physical features, none of them being typical. Now, if you ask what's happening in the universe where a Hubble parameter oscillates and you go from expansion to contraction to bounce, expansion to contraction, then in a classical bounce, not a quantum bounce, you have one feature. Most of the time, the typical feature will be you expand. You contract, that's so contraction. Physical scales contract a lot less than they expand during dark energy domination. So first of all, you solve the why now problem. Where is a typical observer in a cyclic universe? Typical observer has to be in a dark energy dominated phase, since most of the time, all universe will be dark energy dominated. And this is what this is. So it's a physical scales in a cyclic universe. Most of the time you expand, you contract a little bit, bounce, and expand, contract a little bit, and so on. So what really happens is, and this is really the surprising, was what's surprising to us when we asked this question, and it's very surprising to me, and I think it's neat, because inflation was thought to be smoothing because it was somehow reminding us nearly de Sitter type expansion. And if you now look at, but on the global scale, it led to a mess. It is a multiverse or quantum instability problem. And if you ask what is the envelope over multiple cycles in terms of the physical parameter, but what you find is actually a de Sitter-like universe. So the envelope of a cyclic universe is with respect to the physical scale is actually, in some sense, a meta view where space-time is continuously expanding as if it was de Sitter-like, so maximally smooth, as if the evolution on a global scale was driven by something that forces it on being de Sitter, without the local evolution being de Sitter at any point in time. So that perhaps, and I certainly hope that it might turn out to be as a good answer to why we are there where we are today, why our universe looks like, because perhaps it's a cyclic universe that on a global scale indeed looks like as a de Sitter-like universe, exploring phases of slow contraction, bounce, and long phases of expansion, without a bang or a crunch and no beginning and no end. Thank you.
Thank you very much. So let me stop to ask if there are any questions.
I have a question, Daniel, Adi.
Yes, please.
So I am confused about this picture which you have here. I mean, there is a very old argument from the 40s, maybe, by I think Bondi, which says that that since at every cycle the entropy must increase, the universe will increase, and the scale factor will increase, like what you see here, and therefore you will have a singularity at the end, because if you go back in time, you will end up with a singularity as well. And you just said that you don't have a singularity, I think, or what's your take on this?
Thank you. I was expecting that question actually, because there is one difference to the argument of Bondi and Tolman than how you cited it. It's actually the main argument was that earlier, and I don't have here, unfortunately, the picture that I usually show in more popular talks, not to physicists. Actually, the picture was not this, what Bondi had in mind and Friedman had in mind. Up until now, cyclic universes were imagined that not just the Hubble parameter oscillates as it should, but it was imagined that the scale factor also oscillates. So if you look up the Bondi or Tolman model, the real problem was that not just the Hubble parameter oscillates, but the scale factor always returned to 0. So at the bounce, not just H hit 0, but A hit 0. It had to be a quantum gravity regime. Then it again started to expand, then hit 0. And so that was actually the real entropy problem, that you, if everything crunches at the when on average the scale factor is either 0 or crunches and then grows and crunches and then grows, then you really cannot fulfill the second law of cannot comply with the second law of thermodynamics, that the entropy always grows. And so the idea actually what we are promoting here is the opposite. So can you evade this problem by evading exactly the feature that caused the problem, that A goes to 0? if the scale factor never goes to 0, so we know that the scale factor doesn't have any absolute value, it's a conformal quantity, and the only difference is that if it goes to 0 or if it ever goes to 0 or not. If it never goes to 0, you can arbitrarily scale it, its magnitude doesn't have any meaning. We can set it today to 1, we can set it today to 1,000,000, and so on. So just importance is, can it go to 0? And if it doesn't ever go to 0, do we actually encounter this entropy problem? And I would say the dashed line perhaps is one way of seeing why we don't encounter the entropy problem, is because what you do is you let, what you have to ask is what is in your Hubble radius. So what's happening during dark energy expansion, we know everything is just fine, the entropy is decreasing. And then slow contraction happens and the Hubble radius starts, so you just dump stuff. So during dark energy domination, you dump stuff out of your Hubble radius. When you go over to slow contractions, you keep dumping stuff out of your Hubble radius. So the entropy density is remaining exactly in compliance with the second law of thermodynamics, because all the stuff that you would be worried about is dumping. And now you would be in trouble if at the end of slow contraction, you really hit 0. Because if the physical scales hit 0, then all that stuff that you would not worried about that you dumped outside, and that was the real problem, comes into your horizon, because the horizon vanishes, the Hubble radius vanishes, and everything crunches, black holes collide, and you don't really know what happens. That would be the real problem. Then it would really be the case that the evolution of entropy wouldn't be monotonic.
Just a minute.
But if it's not, yes?
I'm starting to lose you. What happens to the entropy density during a bounce and crunch and a bounce in your case?
Yeah, exactly. That's
Simple
a very good question. Okay, good. So you start, so until the bounce, nothing strange is happening. It's all classical relativity. And then that is not the big, what I was coming to. That is not a big divide. If you have a quantum bounce, you have the problem that Bondi and Thorman were pointing out, because your scale factor goes to 0. And during that phase, the entropy really cannot increase. If you have a classical bounce, then you can still, that's maintaining causality, and you can let geodesics go through and you can follow the entropy density, then nothing dramatic will happen. It's exactly the same as following. The entropy is increasing and everything is continuing as it should. Because the point is that the scale factor on average is growing. Nothing is happening to it.
But so you don't have a singularity a long time ago?
I don't, that's the point. Oh, sorry, I should have emphasized it more. Because it's not a singular quantum bounce, but it's a classical non-singular bounce. Therefore, you never reach the quantum region. In particular, you don't have a singularity. Sorry, if I didn't emphasize that, it's my fault, really. That's the advantage why, not just because I don't feel too smart enough to do a quantum bounce. It's also because if you don't have a quantum bounce, you can follow word lines, you can follow geodesics, you can have a entropy density calculation. Yeah, exactly. There is no singularity. So that's the clue at the problem, that it never goes to singular. Yeah, thanks.
Can I ask a question, Daniel?
Yeah, okay, Ares, and I also see that Vincent de Jacques has a question, and then we'll end because we're running a bit late. So yeah, Ares, please.
A quick question. What is the status of observations with respect to inflation or bouncing or anything? Or is there any observational way to verify any of all these theories?
Excellent question. So I always hope that the audience asks the best question. So the entropy was asked, and this is the next excellent question. So verifying is difficult in science, right? So we hope that there are observables that if we find are incompatible with the theory. So that would be the old idea of, can this theory be falsified? And I tend to emphasize that everything. So when we go back to the equation that describes how quantum fluctuations evolve, that also describes the equation how gravitational wave fluctuations evolve, or anything. And what is really the key, or the scalar field energy density, a key is blue shifting. So everything is being blue shifted. There is no quantum instability because the negative Hubble friction, the Friedmann-Robinson-Walker background is blue shifting all energy density, the leading order fluctuations in the scalar and in the gravitational wave fluctuations. And this is the opposite to inflation. Blue shifting means you cannot have a measurable tensor or gravitational wave amplitude from the early universe. And so the experiments that are going on in the Atacama Desert right now in the South Pole, whether it's BICEP 2 or the Simons Observatory that I'm a member of in Chile, or whether it will be CMBS4, whether it will be the Japanese-led Lightbird, they all go after this primordial gravitational wave amplitude signal. Inflation, because there the Hubble damping is a huge positive Hubble parameter, it's redshifting everything. And so there the expectation was, And now it will be difficult. What the real expectation is, the expectation was, and that's why these experiments are going, that should be measured. So one big observable difference would be if it's being measured in the next 5 years, then this scenario cannot be right, because then it's not measurable due to the blue shifting of the amplitude. So you cannot have measurable gravitational waves in the microwave background polarization. So in this, if this scenario is right. So far, we haven't found any. And what if we don't find them? Well, the problem is that inflation is rather flexible. So you have models, you can then adjust the models accordingly. So the one thing that we know, if we find them, this scenario is out, and that will be decided within the next, I would say, 3 to 5 years. If we don't find them, then it looks really good for this scenario. And I'm not the one to say to what extent it's okay to fine-tune inflationary models or not at that point. But one certainly has to go away from favorite models of people where one has already been going away. So this is a falsifiable model, but it's difficult to compare it to inflation because inflation can accommodate both no gravitational waves and gravitational waves.
Thank you.
Okay, Vincent?
Yes, hi. I have a question about initial deviations from non-Gaussianity. How much do your model predicts?
Okay, it's
deviation from non-Gaussianity at, let's say, the last bounce, and how much fine-tuning is there in your model in order to match the latest CMB constraints?
Good. So that's an excellent question. It would really like an hour to give a right answer for you. So I intentionally didn't get into have a mix. I would say that what this model does is the advantages of the model I described. And then now you have to ask, do we have to fine-tune less or more to get the right spectrum? I would say that just as with the gravitational waves, the prediction is very definite. With the density fluctuations, it's similar to inflation. So the only difference being that in inflation, you generate through the features of your potential, tells you what spectrum you get. Here, the leading or in the curvature fluctuations, because the inflation due to the redshift, curvature fluctuations, just like gravitational fluctuations, amplitude remain constant or grow. And you can immediately say what the scalar field does, what's happening to the scalar field directly transform into curvature fluctuation spectrum, that directly transform into temperature and isotropies in the microwave background. So that everything is encoded to what you put into your potential. We know we have to tune it. About the amplitude and for the spectrum, and the one prediction, what the simplest model predicts is almost no non-Gaussianity. In this model, what happens is because everything gets blue shifted, you don't generate curvature fluctuations. What you generate is relative energy density fluctuations. And and that's determined mostly, you simply have a second energy density component, and all the features of what's in the inflation potential, it's all in the second energy density component, which in our case doesn't have a potential, but it's kinetic. It's like a nonlinear sigma type model. So in inflation is the potential, here is the nonlinear sigma type coupling. And I would say, with respect to that, apart from the one doesn't predict the multiverse, the other is the same amount of tuning. So that is not for the fluctuation spectrum. So near scale invariance and the amplitude, just like in inflation, has to be dialed in. And for non-Gaussianity, as in inflation, in single field inflation, there is no measurable non-Gaussianity predicted in this model because it's so what we are pursuing is a kinetic coupling, no potential. So it's almost a massless, nearly massless or massless second field. That is, the prediction is up until the bounds, no non-Gaussianity. And what we are computing right now is we expect the order 1 contribution from the bounds because that will be nonlinear. So if there will be, that's why we are doing the whole simulation. We do expect that there will be an order 1 contribution, and we hope that will make it even, again, observationally falsifiable from inflation, where there is no measurable contribution. So I cannot yet name you the number, but it's the right intuition that the bounds itself should add some nonlinearity.
Okay, thank you very much.
Okay, well, I'd like to just thank you very much for this very interesting talk, and for whoever is interested. So the seminar will be which day?
I was invited for Wednesday, and I cannot tell you the moment, the link, or the time.
Okay,
it's Wednesday, yeah. Wednesday 3:30, I think.
Okay, thanks. I'm sorry about that. Yeah, but I will be there.
Okay, well, thank you very much.
Thanks very much. Thanks for the invitation. Thank you.
Bye-bye.
Thank you very much.
Bye-bye.
Bye-bye.